Section 12.6, triple integrals and cylindrical coordinates, video 3. All right, so let's see how to set up and evaluate a triple integral in cylindrical coordinates. In the previous series of videos, we talked about three types of solids. Type 1, where the top and bottom of the solid were bounded by functions of x and y. Number 2, and honestly I get 2 and 3 switched sometimes, but another one was, we'll call it type 2, where the left and the right sides of the solid were bounded by equations of the form y equals some function of x and z. And the third type of solid was where our solid was bounded on the front and back by equations of the form x equals some function of y and z. Because we're only looking at polar coordinates in the xy plane, we're going to focus on what was called the type 1 solid, or type 1, I said type 1 integral here, but it was type 1 solid, where the top and the bottom of the solid are bounded by functions of x and y. It's possible to do type 2 and type 3, but in cylindrical coordinates, what you would want to do is you would not want the polar representation on the xy plane. If you were doing type 2, where your equations were bound on the left and the right, or your solid was bound by functions on the left and the right, then you would want the polar coordinates to be in the xz plane. And if you had a type 3 solid that was bounded on the front and the back by functions of, that would be functions of y and z, then you would want the polar representation to be back on the xz plane. But we'll keep it pretty simple. It's just a matter of we're looking down the xy axis for our region. All right, so we're going to look at solids that are bound on top and bottom by functions of x and y. So as before, we'll call the top function u2 of xy and the bottom function u1 of xy. And since we're talking cylindrical coordinates, which is polar in 2 dimension, then our region down in the xy plane will be defined in terms of polar coordinates. Cylindrical, if you want to think of it embedded in 3 dimensions, where the surface in the xy plane, the radii are defined as functions of the angle. So we'll call the inner radius function h1 of theta and the outer radius function h2 of theta. And of course our thetas are just bounded between 2 constants. We'll call them theta 1 and theta 2. So how do you do a triple integral? Well, same way we've always done a triple integral. We start by doing a single integral in the direction of the functions that are bounding, in this case, the top and the bottom. So it's going to be a dz integral. And then our limits of integration will be u1 xy and u2 xy. Now, what about the function in the middle? Well, we'll leave it f of x, y, z just for the moment, because we're not really doing anything with r's and thetas there. And then after we do the single integral in the z direction, then we do the double integral, didn't space this out very well, over the region dA. But the double integral is going to be in polar coordinates. So how do we do that? Well, when we do the double integral in polar coordinates, we're going to do dr first. This is after we've done the dz. And the r's are going from the inner radius, which is h1 theta, to the outer radius, which is h2 theta. And then we're going to do the d theta last. So that's going from theta 1 to theta 2. Now, our inner integral is still dz, but this is where it's going to get a little jacked up, and I'm going to need to make some room here. I'll put the dz, dr, d theta over there. It's going to get a little jacked up for 2 reasons. Number 1, don't forget, in polar coordinates, when you're doing a double integral, you have to bring in an extra r. That doesn't change here. We're still doing a polar integral, polar double integral, when we do the double integral down here in the xy plane. And so we have to bring in the extra r. That's easy to forget. Number 2, inside the function, we have to change everything to cylindrical coordinates. x is equal to r cosine theta, y is equal to r sine theta, and z is just equal to z. And in the limits on the first integral that we did, the limits up here when we did the dz integral were functions of x and y. But when we convert it to polar, we have to convert, cylindrical, we have to convert those x's and y's as well. So the upper limit on the first integral becomes u2 of r cosine theta, r sine theta. And the lower limit on the first integral becomes u1 r cosine theta, r sine theta. So basically, everything gets converted. All the x's become r cosine thetas, all the y's become r sine thetas. The differential picks up the r because of the double integral in polar coordinates, and we get a great big mess. This will make a lot more sense when we actually do an example, but it's just the same idea as before. To do a triple integral, do a single integral in one direction, in this case the z direction, from bottom to top, followed by a double integral in the plane where you project in the z direction, which is onto the xy plane. But when we do the double integral, it's in polar coordinates, and therefore we pick up the r, and all the x's and all the y's change. Let's take a look at an example.